So let me start with first saying about the people who carry out the work or the collaborators. So this work really started when I worked with Garnet Chen at Caltech, and throughout the years, many great collaborators, including Lin Qingpeng, Huanchen Zhai, and Zhihao Cui, all from Garnet's group, and also more recently we did some new development of this full cell DMFT scheme by my postdoc Jiacheng Li at Yale. All right, so let me first just start with a really short one-page introduction to DMFT because I think this audience doesn't really need a lot of that. Essentially, DMFT is designed in a way that maps a correlated lattice problem into effective impurity problems. And in its original single-side formalism, you get a single impurity site coupled to infinite bus and through hybridization function. And then this embedding problem can be solved by any high-level impurity solvers that you like. And the true power of DMFT is because it has this local self-energy correction approximation. Then for strong local electron correlation problems typically seen in many correlated materials, it can work really, really well. And there are also many formalisms that tries to extend single-side DMFT to account for non-local electron correlation. Here are just the two sort of most commonly used extensions: cluster DMFT in real space and the DCA, D gamma A in reciprocal space. But here, today my focus will be to do ab initio DMFT calculation. In that sense, we will use DMFT to mean both single-side and cluster DMFT in this talk. Before I really introduce what is full cell DMFT, I want to motivate our development by just going through what's a common formalism for doing ab initio DMFT for materials. And that is the downfolding formalism. So here, this is my understanding of the downfolding formalism for ab initio DFT plus DMFT or GW plus DMFT. So what you do is you start from a DFT calculation of the band structure. You choose a low energy subspace and you downfold it to a small correlated space. That's typically a few strongly correlated orbitals like D or F orbitals. And then you use a few or even one parameters describing the Coulomb interactions. And you can choose many different kinds of impurity solvers, but for many applications, it's typically continuous time, quantum Monte Carlo, or its variance at finite temperature. And this setting is very successful. It has been used for study many challenging, strongly correlated electron systems and definitely gain a lot of useful physical insights into these problems. But what motivates us is really what are the existing challenges in this formalism? And to us, we think probably the most important challenges are the following. The first is downfolding, because we use approximate numerical procedures like constraint RPA or constraint DFT. It inevitably can introduce some uncontrolled errors in the impurity Coulomb interactions. And then second is that if we take a step back, then when we start by constructing the correlated orbitals on the impurity subspace, we can even have this kind of ambiguity so that the results can be sensitive to this choice. So here is an example from Andy Miller's paper a few years back, where they used DFT plus DMFT to study neodymium nickel oxide. And in this paper, what they show is that if you just look at the mass enhancement for this nickel Eg band across a Fermi level, then you find that by constructing this embedding problem, or the impurity orbitals, really, using 4 different ways, and then everything else is pretty much the same, you can actually get a range of mass enhancements for this same calculation. Essentially, no matter what you do in local orbital basis or in a band basis, you can find a twofold difference when you use different ways to construct this problem. And if you use CRPA interaction parameters for different kinds of construction, the difference can be even larger. And there are also some other problems associated with this formalism. I don't think they are always there. You only encounter this kind of problems for specific problems. For example, sometimes you may need better treatment beyond DFT and GW for intermediate range correlation. And sometimes the CTQMC solver may be limited to certain type of general interactions or low temperature. And also, of course, there's double counting issue in many DFT plus DMFT calculations. So these are the really points that motivates us to think about the following question, is that a DFT provides a really powerful theory. And in order to use it for more predictive and also more general toolbox for all sorts of different correlated electron materials problem, then probably we want to think, can we design another formalism that does not have many of the challenges here, so that this typical, this new formalism can be useful or can make this toolbox even powerful. And that is why we introduced this full cell quantum embedding framework. So before I start to talk about the DMFT, I want to mention we actually developed this same formalism not only for DMFT, but also density matrix embedding theory led by Zhihao Cui, currently at Columbia. But today I'm going to be focusing on DMFT. The idea is pretty straightforward, actually. Is that instead of doing downfolding, what we do is we select a given unicell or supercell. Then we say we're going to just include all local orbitals confined in this unicell as our impurity. That means if I take this cuprate material as an example, I will not only choose copper 3D orbitals into the impurity problem, but also I'm going to choose oxygen 2p, or even some high virtual orbitals like oxygen 3d, copper 4f, so on and so forth. And that results in a very large impurity problem compared to before, the downfolding formalism. Typically, this setup can give you tens to even 100 impurity orbitals. And because of that, there's no need to downfold. Because we're just going to treat a general bare Coulomb interaction between all of these impurity orbitals using impurity solvers. And because of that, also non-local electron correlation that's typically medium-ranged, that's not that easily captured by downfolded DFT plus DMFT formalism can enter the theory. And I want to put a short note here that we think that full cell DMFT can be considered as an all-orbital version of cluster DMFT. All right, so of course, this is very different from what people typically do DMFT. So I want to talk a little bit about the underlying infrastructure that enables this formalism. First of all, we rely heavily on the PyACF package developed by Garnet and also Tim and many people now, where all of our periodic calculations are actually built on top of a periodic Gaussian atomic orbital basis. And on top of that, there are all sorts of low-level methods such as Hartree-Fock, DFT, several variants of GW methods built in using this basis. And more specifically to DMFT, we use several kinds of quantum chemistry-inspired impurity solvers, such as couple cluster theory, also quantum chemistry, flavor of DMRG, selected configuration interaction. And we have put these two libraries for embedding specific techniques. All right, so let me dive deeper into the formalism. First, I'm going to talk about two different impurity solvers that we use. One of them is couple clusters theory. Because of the time here, I'm not really going to describe the underlying algorithm. But a one-line equation here shows you that the couple cluster is a wave function-based theory. It has a exponential parametrization of the wave function, where this T operator here really is a summation of a series of particle hole excitation operators. Throughout years, we actually have, or many other people have benchmarked the couple cluster theory in different situations. Here I'm showing you two. On the left, this is the Simon's benchmark back in 2020, where people look at many different methods for transition metal monoxide molecules. Here I'm showing you that two flavors of couple cluster. This is couple cluster singles, doubles with perturbative triples, nearly exact compared to DMRG and the SHCI, where the cheaper CCSD method also get a pretty reasonable accuracy. On the right-hand side, I'm showing you a benchmark we did with Tim and Garnet back in 2019, where we studied simple Harmon model problems using a very standard single-sided cluster DMFT with CCSD impurity solver. Here I'm showing you 1D Harmon model result, where CCSD solver agrees quite well with AD solver. All right. Using that solver, we studied a few different type of material problems. Here I'm showing you one of them as a validation for this full cell DMFT framework. And more specifically, I'm showing you full cell GW plus DMFT calculation on nickel oxide. We start from a one-shot GW calculation, which fails for this type of transition metal oxides. The band gap is very small compared to experiment. But when we do this full cell GW plus DMFT using a nickel oxide AFM cell, which has two nickel oxide units, we include every orbital in that unit as our impurity. We gain pretty good description of the spectrum, not only in band gap, but also the spectral function agrees quite well with experiments. And of course, this is some pretty old data nowadays, actually. So today I want to show you some new developments. Before
you move on, can I ask a question about the last slide?
Sure.
So couple cluster is a single reference quantum chemistry method, and antiferromagnetic coupling you would think would be like a deeply multi-reference problem. Do you have any intuition for why this works so well with couple cluster?
Yes, so the thing is actually the symmetry breaking helps couple cluster. We have found that, so here this CCSD method is a symmetry broken CCSD, a spin unrestricted one. And we find that when you have more like ordered phases, symmetry breaking actually helps a lot. And couple cluster theory works quite well for that scenario. And if you're truly dealing with a problem without symmetry breaking, then CCSD may break down for a lot of like multi-reference character. Yeah, your question is very valid. And that is why I'm going to talk about the MRG solver in a minute. Yeah.
Thank you.
Yeah. All right. So as we just discussed, right, couple cluster theory is good for when you have a really large number of moderately correlated orbitals, but it is not a method of choice if you have truly strongly correlated problems with what we say multi-reference character in quantum chemistry. And in that scenario, we turn to a more numerically reliable or robust method like DMRG. Here, I just want to mention this new implementation for DMRG, optimized for quantum chemistry Hamiltonian, led by Huancheng Zhai, a great postdoc in Gardner Chen's group, where there's now a new code, block 2, that is really a high-performance DMRG code, has favorable scaling for very general quantum chemistry type Hamiltonian, and also can scale to thousands, of course. And this will be our main solver for the next 2 applications that I will talk about. And the first one is I want to go back to this problem about neodymium nickel oxide. Here we're studying a material slightly different, lanthanum nickel oxide, because we want to avoid complicated 4f orbitals here. So we just focus on this lanthanum one. And we ask the question, if the unfolded DMFT can give you this uncertainty, can we reduce this uncertainty by doing the full cell DMFT? Or here, sometimes I will use the name all orbital DMFT. What we do is actually quite similar to what Andy's paper did. We are going to really construct the local orbital bases using 4 different flavors. 2 of them are the same as in Andy's paper. These are the maximally localized linear functions, selectively localized linear functions. The difference between these 2 is you select only to optimize 3D orbital extension for every orbital in your impurity, or in your subspace, to be more accurate. We also use 2 other methods that's first is intrinsic atomic orbital. This is actually the default basis in full cell DMFT, and the Loveday orbital, which is really crude and not supposed to be good local orbital basis. Okay, so here is the result from a full cell GW plus DMFT calculation. So we use the same color bar as in this paper. And if we just focus on this band that crosses Fermi level, which is dominantly a nickel dx squared minus y squared orbital character, we find first, by just looking at this figure, the color coding of this band is essentially the same across 4 different construction of local orbital bases. And if we just look at the numbers at a specific point, which is this x point band basis, and to calculate the mass enhancement, here is the result. And you see that the GW plus DMFT calculation constantly gives around 3.4 to 3.6 for the mass enhancement, meaning that the uncertainty or the difference between this different type of constructions is largely reduced compared to before. So this is one case where we show how full cell DMFT can help to reduce some uncontrolled errors in previous formalism. And next, I want to show you another application we did for simulating a prototypical strongly correlated problem, which is the Kondo problem. And for the Kondo problem, I think I don't need to introduce much about what is this problem. But instead, I'm just going to focus on what we're going to study, which is we're going to study a series of 3D magnetic impurities in bulk copper. And here, this is an old experimental measurements of this Kondo temperature for different type of impurity. And in the first place, probably the most obvious trend is this exponential Kondo temperature difference across different impurities, and they can be as different as three orders of magnitude. And of course, this problem is very well known now. This exponential trend or the suppression of Kondo temperature is due to Holmes-Root coupling, nicely summarized in this review article by Anton and other colleagues. But in the numerical simulation, or what I want to put is ab initio prediction of Kondo temperature across a range of different type of impurities is still very challenging. And of course, over the years, people have applied different type of DMFT-based techniques to tackle this problem and gain various results. Here is just a very incomplete list of that. But what we want to see is if we want to argue our formalism can be used for really challenging correlated electron problem, and probably we want to study this one first and see how far we can push our methods for such a problem. Here's our strategy. I don't want to spend too much time for the details, but to tell you a little bit about the setup, what we are doing here is we're choosing all local orbitals associated with this impurity atom as our impurity in the DMFT calculation. That being said, all of these orbitals shown here are impurity orbitals. And we are coupling those impurity orbitals, and more specifically, we mainly couple the valence orbitals to a large number of discretized Bass orbitals because we're going to use Hamiltonian-based solvers. A note here is that although we are only doing local orbitals on this impurity atom as our impurity, as you can see here, when we construct these local orbitals for orbitals like 4s, 4p, and 5s, because of their more delocalized nature, actually they extend to neighboring atoms. In that sense, our Hamiltonian actually also includes certain level of interactions, or more specifically Coulomb interactions between an impurity atom and neighboring copper atoms. And our solver will be DMRG. And of course, for this very large impurity problem, over 300 orbitals, there's no way that we can really solve it with brute force DMRG. So what we are doing here is actually we introduce a natural orbital-based active space scheme. So we do a three-step procedure to bring down the complexity of the problem. So what we do is we solve this whole problem using a truncated CI method that is CI singles and doubles. We derive natural orbitals from the CISD calculation and to reduce it to a tractable size for the MRG. And we do another round of this to even bring it down so that we can do dynamical DMRG, where the Green's function calculation is much more time consuming compared to the ground state ones. All right. So here I'm just showing you a brief picture about one of the spectral function we get. This is iron in bulk copper. And these are the orbital resolved spectral function for iron impurity. As expected, right, we got a Kondo resonance that is very sharp around the Fermi level. and you have also some side bands on both sides. But before I go really into claiming any quantitative comparison, I want to show you one careful check whether this strategy really gives you reliable prediction, which is we introduce this active space sort of scheme. So I want to make sure the active space we use for DMRG is reasonably good. That's why we did this careful benchmark for all impurities where we say, okay, we use a strategy, but then we increasing the active space treated by DMRG gradually and see how our quantities converge. Essentially, we want to know if the 3D orbital occupancy and the quasi-particle weight for the 3D orbitals for the impurity are really converged to a good level that we can confidently compare to experiments. And here, as you can see, I'm showing you 3 cases of them. Actually, for most of the impurities, we're pretty confident that they are converged to a decent level of accuracy to the parent basis result. And the only exception is manganese, where we cannot do larger active space beyond 22 electron 22 orbital because the DMRG bound dimension needed for the dynamical DMRG is too large. All right. With that, I want to show you the prediction of conduct temperatures compared to the experiment results that I just showed you. Here we use a pretty standard method to extract conduct temperature in this field, which is to use Hugheson's renormalized perturbation theory of Anderson impurity model, where you just need to compute the quantity, which is quasi-particle renormalization and DFT hybridization at Fermi level. And on the right is the theory prediction compared to various of experimental measurements. The first thing is that the experimental conduct temperature trend, the exponential trend, is well captured by the prediction, which is a good sign. And also, if we focus on some more challenging impurities, such as manganese, chromium, and iron, we find that the subtle trends between these different impurities are also captured. For example, chromium has a lower conduct temperature than iron, as measured in the experiments. We find that this kind of subtle trends is due to orbital-specific conduct physics plotted here. So if you look into the quasi-particle renormalization for T2G versus EG orbital, we find the low conduct temperature in chromium is pretty much T2G driven, while the low conduct temperature in iron is more EG driven. Same thing for manganese. And of course, you see discrepancy in the simulation. The main discrepancy here is that the low conduct temperature impurity prediction is not really that quantitative, specifically for manganese. And we think, and we checked the main problem is really the DMRG active space, that we cannot go to a larger active space for manganese. So we cannot really confirm whether this calculation is really converged to its parent basis limit. And of course, we neglect a certain level of long-range interactions beyond the nearest neighbors that certainly contribute to the errors. But because of the other impurities are in pretty good agreement, we think these long-range interactions do not really contribute significantly to the errors for the predictions. Okay. One more thing about the conduct temperature prediction is the following, is that we want to ask the question, what if we use a downfolded strategy for the same problem, right? So here we did our own version of downfolded model Hamiltonian, where we use 5 3D orbital as impurity, and we adopt a pretty standard Hamiltonian, Kanamori Hamiltonian with UJ values derived from constraint RPA. And we just applied the same DMRG solver and active space scheme for tackling this problem. And the results are shown in this brown circles. The first thing we observe is we did not observe a clear condo temperature trend compared to the experiments or the orbital calculations. And also the second thing we observe is that the condo temperature is typically overestimated compared to the other two. And compared to the orbital calculation, the difference sometimes can be as large as 1 order of magnitude. All right, so this is a condo temperature result. Finally, hope I'm gonna use 3 to 5 minutes, hopefully, to talk about a new development, and I'm pretty much done. So the new scheme that we recently developed is something called interacting bus dynamical embedding. The philosophy is the following. Up until now, right, to the counter problem, what the full cell DMFT scheme is doing is really saying, I will choose a reasonably large impurity problem, and then I don't need to worry about a lot of downfolding associated parameters. And then in those cases, we just use standard way to discretize our Bass orbitals. But in this new development, we think about the Bass part, right? If now we have we think a good control on the impurity part, can we do better for the Bass part as well? So that is what motivates us to do this development, where what we're trying to do is we want to systematically expand the Bass representation in real space surrounding a chosen impurity atom through cluster-specific natural orbitals. I don't have time to go into details, but we are really inspired by this PRX paper from George Booth. And as you can see here, what I mean is really by using systematic expansion of this Bass, you can actually draw in real space so you can visualize it. That means you can actually write down a projection between the full Hamiltonian to this Bass space. So here, this is an illustration of that. You have your impurity block, you have your Bass block. So you can write out this rotation matrix so that you can just rotate your full Hamiltonian into an embedding Hamiltonian. In that sense, you can actually include the general two-particle interactions on both impurity and Bass sites. That's why we call this method the interacting bus embedding. The nice thing about this theory is that it can capture longer range electron correlation even beyond the previous full cell DMFT. And also a nice thing is it preserves translational invariance almost perfectly. So there's no translational symmetry breaking as seen in previous cluster DMFT calculations. I want to show you one application about this method, which is not a strongly correlated problem, but a very, people think this is a long-range electron correlation example, which is metallic sodium. This has actually been studied by various DMFT methods over the last 5 years. So here, quickly speaking, what is this problem? The problem is that when you use DFT method like LDA or PBE to describe the sodium occupied bandwidth, you always find an overestimation, no matter what DFT you use. And the overestimation can be quite large. If you use perturbation theory like GW, you can gain an improvement, but the improvement is relatively small. So people are debating whether you need to add dynamical electron correlation either in a local approximation or more aggressively local and non-local dynamical electron correlation. So here, what we're doing in the latter, which is using this new embedding scheme, we're really including quite long-range electron correlation at couple cluster level into the theory. And then here is a result on the left. The heat map is a simulation from this new theory. And we're comparing to PBE, G0W0 at PBE, and these other two experimental R-pace measurements in black dots and red curve. So you see this photo emission spectrum agrees quite well with the experiments. If you measure the bandwidth, it's largely improved over GW and in a pretty good agreement with experimental bandwidth. And some insights from the simulation is the following. We find that if we really look into the sodium or 3S self-energy correction that is non-local or longer and longer range in real space, we find that this self-energy correction between GW level do not really decay to zero beyond until fifth or the sixth neighbor. That means this correlation is indeed quite long range, and we think correcting or capturing this correlation beyond GW level is crucial for quantitative prediction of bandwidth. All right. With that, I want to conclude. I have shown you 3 examples of this framework, including Nicolet, Kondo, and the metallic sodium problem. And the philosophy, again, in this theory is that we want to introduce another formalism that we can gain better control of our simulations and hopefully treating local and non-local electron correlation on equal footing. And with that, I want to thank you for your attention, and I'm happy to answer any questions.
Okay,
thank you very much,
Tianyu. Go ahead, Olivier.
Yes, just wanted to say that we have about 5 minutes for questions, so please raise your hand. The first one is Antoine.
Yeah, so I'll try to be very quick. Tianyu, can you explain in this full cell approach how you handle the matrix elements of the interactions in which not all 4 indices of the matrix elements are within the same cell? So
yes. So in the full cell formalism, the handle of that is pretty much same as cluster DMFT, meaning that beyond the cluster that you choose or beyond the cell you choose, you don't have any general interaction, like Coulomb interactions between the impurity orbitals and any orbitals outside it. And everything account for it is just hybridization function. And that part is pretty much same as what you do for model Hamiltonian when you do, say, for example, cluster type. You have Coulomb interactions within cluster, but nothing beyond that.
And you're not treating those at the Hartree-Fock level, for example.
Oh, in that sense, we are. We are treating that at Hartree-Fock level, but we don't have any
dynamics.
So, yeah, we don't have any dynamical treatment beyond.
Okay, so
that.
intercell is treated more or less Hartree-Fock, and then intracell is treated fully dynamically. Thank you.
You can certainly also include GW for the intercell if you want. Yeah.
Thank you.
George, you're next.
Thanks a lot. Can you hear me?
Yes.
Yeah, brilliant. Hi, thanks a lot, Tianyu. Really nice talk. I just wanted to ask a little bit about the interacting bath stuff at the end, and yes. Thanks for the shout out. I wanted to ask, so we've been investigating similar things. One of the difficulties is that an interacting bath projective formulation, which is the way I kind of think about it, is incompatible with the normal self-consistency that you would normally think of in DMFT, as far as we can see. in that you have a fully self-consistent dynamical local self-energy. So I was just wondering if you were doing any kind of self-consistency with this, and if so, what type of self-consistency were you doing?
Yeah, that's a very good question, George. So the short answer is, for the results we're showing here, we are only doing a one-shot calculation. So
Okay,
it's really
makes sense.
not self-consistent one. The thing is, what we do is actually a similar strategy to the counter problem. We systematically increase the thing and we check whether the quantity is converged. And probably because the problem we study here is not really strongly correlated problem, that maybe self-consistency is not that important here. But you are certainly right. If you're gonna apply this method to really correlated problems, and self-consistency can be important. And I don't have a good answer for that.
No, I think that was a good answer, frankly,
Yeah,
and
yeah.
it kind of reflects my thinking as well, right? I mean, there are going to be times where that full dynamical self-consistency is important, and times where it isn't, and if it isn't, then maybe long-range correlation is more important. So I think it's yeah, I think it's an interesting approach. Thanks.
Mm-hmm. Thank you.
The next question is from Tim.
Hey, Tianyu, great talk. My question is about the DMRG impurity solver. So the extra narrowing of the orbital space that you have to do the spectral function.
Mm-hmm.
So the impurity solver with DMRG is done in the like correction vector sense, I assume, of like solving a linear system of equations for the response. So is it that for some reason just doing that instead of the ground state eigenvalue problem is expensive, or that like the bond dimension for the response vector has to be larger than the bond dimension for the ground state eigenvector?
I think it's a former one. It's a former one, because we're solving the problem on the real axis, and the condo around the Fermi level, the counter resonance is really, really sharp, meaning that you need to use extremely small broadening factor and also extremely dense fast discretization. And those all make this problem much harder than a typical spectral function calculation, actually.
I see. Okay. I'll save the rest of my question for another time. Thanks, Tianyu.
Yeah.
And the final question will be asked by Hangwei Chen.
Oh, hi. Tianyu, it's great talk. Can you go back to the slide where you show the math enhancement of length Nicolate?
Yes. This one?
No, go one more. Yeah, this one. Yeah, excellent. So when you compare to Andy's work, I believe that you probably use the same U value. So can you comment on that? Why your effective mass is substantially smaller than Andy's results?
Okay, so yeah, here, this is Andy's result. This is our result, right? So first of all, we did not use any U or J parameter, because what we do is actually, although we construct the local orbital in the same way, what we do is actually we include every orbital within this Nicolate unicell into our impurity, meaning that instead of two impurity orbitals in this calculation, we have more than 30, 40 impurity orbitals. And in that sense, we just directly use unscreened Coulomb interaction as you can calculate directly. And then that is a major difference. And the results we got actually, right, if you look across Andy's result, our result are actually agrees well with some of their schemes, not every scheme, because they have this uncertainty. Yeah.
But does that mean that, so compared to Andy's result, does that mean that this called selective localized Deweynian function probably is better compared to the more traditional maximum localized Deweynian function? So the second one, the SLWF is closer to your result, right?
That I
While the-
cannot, yeah, that I cannot really claim because I cannot exclude the possibility of some error cancellation in that SLWF calculation because we did not perform that one. So I cannot claim that one is better. But
Alright.
the observation is the results are similar. Yeah.